Some of the world's oldest buildings are also the toughest. For thousands of years, ancient temples have stood firm in the very places modern engineers fear most, the earthquake zones that shatter concrete and steel. This video is an investigation into a forgotten science, the ingenious principles that let monuments like the Parthenon, Angkor Wat, and Japanese pagodas survive catastrophic quakes. By the end, you will understand the hidden rules of survival that kept these stone giants standing, knowledge that could reshape how we build today. How did builders without computers or physics create structures that dance with the earth instead of fighting it? And what crucial lesson have we, in our age of rigid skyscrapers, potentially overlooked? The answer lies in a radical idea that true strength is not about being unbreakable, but learning how to bend. What does endurance truly look like when the ground itself turns against you? The ground does not simply move during a quake, it transforms into a weapon. An earthquake is not a single force, but a cascade of destruction. First comes the violent shaking, a side-to-side and up and down lurching that can rip the foundations from under a building. Then, in areas with loose, wet soil, the trembling can trigger liquefaction, turning solid earth into a temporary, churning liquid that swallows supports whole. On slopes, entire faces of mountains can shear away in landslides, burying everything in their path. Modern engineering fights this chaos with immense strength, using reinforced, rigid, unyielding structures. The goal is to resist, to stand absolutely firm against the onslaught. And when the quake is powerful enough, that very rigidity becomes a fatal flaw. The structure, unable to flex, concentrates the immense energy until something snaps, a column shears, a beam fractures, and the whole system collapses. This is the expected outcome, the inevitable result of a battle between an immovable object and an unstoppable force. Yet history presents us with a profound contradiction. Scattered across the planet's most active fault lines, in the shuddering Mediterranean basin, along the crumpled spine of the Himalayas, and throughout tremor-ridden Japan, stand monuments built of stone and brick that have witnessed centuries even of these exact events. They are not immune. Their surfaces are oftened by time and tremor, but their essential form remains. They have endured where logic says they should have fallen. This is the central paradox of our story. How did these seemingly brittle, heavy structures, assembled long before the science of seismology existed, learn a different way to survive? Their longevity suggests they were not fighting the earthquake at all, but engaging in a far more sophisticated dance. The Parthenon offers our first concrete clue in this ancient puzzle. Perched high on the Athenian Acropolis, this temple has overlooked a city shaken by countless tremors for 2,500 years. The ground beneath it is far from stable, yet its iconic columns remain, a testament to a design philosophy that embraced movement, not defiance. If you look very closely, you will see that nothing about this building is perfectly straight. Its entire base, the massive stone platform called the stylobate, has a gentle, almost imperceptible upward curve. This was not a construction error, but a brilliant piece of optical and engineering genius. By arching the foundation, the builders created a structure that was inherently more dynamic, less likely to act as a single, brittle slab. When seismic waves passed through, this curvature helped distribute the forces, encouraging the building to sway as a cohesive unit rather than crack apart at a rigid seam. But the real secret lies in the connections. Each towering column is not a single piece of marble, but a stack of individual drums, carved and fitted with astonishing precision. They were not simply glued together, they were joined with a hidden system of flexibility. Iron clamps, shaped like double T's, were set in lead pouches to connect the drums horizontally, while central wooden dowels aligned them vertically. The lead was the key. It acted as a cushion, a malleable buffer that allowed the stone components to shift and grind against each other without shattering. During an earthquake, these columns were designed to behave not as rigid pillars, but as assemblages of independent blocks, each one able to rock and settle independently, dissipating the violent energy through friction and minute movements across countless tiny joints. It was a system of controlled, graceful disintegration, where the building was permitted to come apart just enough to avoid catastrophic failure and then settle back into place. The metal clamps kept everything connected, but the lead ensured they were not locked in a death grip. This is the essence of seismic wisdom, building with the understanding that some give is necessary for survival. The Parthenon was engineered to be a living structure on a living earth, its strength derived from its ability to dance. This stacking of stone drums was not a compromise, it was the core of the seismic defense. Think of a modern concrete column as a single, rigid baseball bat. If you strike it hard enough in the middle, it will snap cleanly in two. Now imagine that same bat is instead a stack of thick hockey pucks, bound together by a strong but flexible strap. Hit that stack with the same force, and the pucks will slide against each other. They will rock and jostle, absorbing and dispersing the impact energy across every joint. The stack might bend, but it is far less likely to break. This is precisely the principle at work in the Parthenon's columns. Each drum, weighing several tons, was meticulously carved so its surface was not perfectly flat, but slightly convex, creating a contact point only at the very edges. This meant the massive weight of the column above was concentrated on a narrow ring, maximizing the friction that held everything together under normal conditions. But when an earthquake's waves began to roll through the hill, that friction became a dynamic tool. The energy from the shaking would overcome the static friction at these joints, allowing the drums to slide minutely against one another, to rock and pivot. This movement converts the devastating kinetic energy of the quake into other forms, primarily heat and sound, through the grinding of stone on stone. The stress that would have built up and shattered a monolithic column is instead dissipated across dozens, even hundreds, of these micro-movements throughout the entire colonnade. It is a brilliant example of distributed failure, where the structure is designed to sacrifice perfect stability in 1,000 harmless ways to preserve its overall integrity. The building essentially trembles along with the earth, its components engaging in a carefully choreographed shuffle that prevents any single point from bearing the full, catastrophic load. This ancient understanding of friction and flexible joints reveals a humility before nature's power, an acknowledgement that sometimes, to stand tall, you must first learn how to sway. Across the world in Japan, the same principle of flexible strength found an even more elegant expression in wood. While the Parthenon used stone drums to dissipate energy, Japanese master builders confronted a different, terrifying reality, constructing towering pagodas up to 5 stories high from interlocking wooden joints. In a land plagued by some of the most powerful earthquakes on Earth, logic would dictate these tall, top-heavy wooden towers should be the first to fall in a major tremor. Yet historical records and modern observations tell a different story. These graceful structures have survived quakes that flattened modern concrete buildings around them. Their secret weapon is not hidden in the joints, but hangs in the very center of the building, a single, massive pillar known as the. This central column is the pagoda's beating heart and its genius shock absorber. In many of the most resilient designs, this pillar is not anchored to the ground at all. Instead, it is suspended from the apex of the roof, dangling like a giant pendulum down through the hollow core of the building, its base hovering just above the foundation floor. During an earthquake, the entire wooden frame of the pagoda begins to sway, each story rocking in a complex snake-like motion. But the suspended, due to its inertia, wants to stay put. As the building sways to the left, the heavy central pillar lags behind, pulling against that movement. Then as the building sways back to the right, the pillar swings the other way, creating a counter force. This dynamic opposition acts as a massive, passive damper, constantly checking and calming the building's oscillations. It is a breathtakingly simple application of physics, transforming a potential point of weakness, a heavy central mass, into the very source of stability. The building does not resist the quake. It incorporates the quake's energy into a balanced dance between the flexible frame and the oscillating weight, a dance that ends not in collapse, but in a gradual, gentle return to stillness. The suspended pillar reveals a deeper truth about these ancient designs. They fundamentally refuse to fight the moving earth. This philosophy extends beyond the pagoda's core and into its very feet. Many of these towering wooden structures are not anchored deep into the ground like a modern skyscraper. Instead, they often rest on top of large, rounded stone bases, sitting upon them rather than being rooted within them. It is a principle of deliberate detachment, a floating foundation. When seismic waves roll through the soil, these large foundation stones can rock and shift independently. This movement acts as a first, critical buffer, preventing the full, jarring force of the ground's lurching from being transmitted directly into the wooden frame above. The building is, in a sense, isolated from the worst of the tremor's violence. It is a stunningly simple concept: isolate the precious structure from the dangerous ground. Today, we recognize this exact idea as one of the most advanced techniques in seismic engineering, called base isolation. Modern buildings, from hospitals to museums, are now sometimes built on massive rubber and steel bearings that allow the entire structure to slide horizontally during a quake. The goal is identical to the ancient builder's intuition: to let the foundation move so the building doesn't have to. Seeing a 5-story pagoda resting on stones and a billion-dollar hospital mounted on high-tech pads reveals a through line of human ingenuity spanning centuries. Both systems acknowledge the same profound wisdom, that sometimes the safest thing a structure can do is not stand rigidly against a force, but step gracefully out of its way. This concept of building with flexibility, of designing structures that could move as a single, resilient entity, echoes far beyond the temples of Greece and Japan. It forms a recurring pattern, a kind of architectural intuition that emerged independently across continents. Nowhere is this more visually stunning than in the mountains of Peru, where the Inca builders mastered a technique so precise it defies belief: polygonal masonry. At sites like and the fortress of, you will find walls built not from uniform bricks, but from massive, irregularly shaped blocks of granite. Each one uniquely carved to fit perfectly with its neighbors in a complex, 3-dimensional stone puzzle. These stones interlock with such tight seams that, famously, not even a blade of grass can slip between them. But the genius is not just in the precision, it is in the purpose. These walls were built without any mortar, the binding agent we rely on to hold modern masonry together. And that is exactly the point. A mortar joint is rigid, it cures hard and brittle. When the ground shakes, that rigid joint becomes a line of weakness, a place where the wall wants to crack. The Inca system eliminated that weakness entirely. Each irregular stone, with its dozens of unique angles and facets, locks mechanically into the stones around it. When seismic energy travels through such a wall, it has no straight, continuous path to follow. The force is diverted, shunted laterally through a labyrinth of interlocking faces. The entire structure can shift and settle as a cohesive mass, the stones grinding and settling against one another, redistributing the load dynamically. It is a wall built to dance, where every block is both supported by and supporting its neighbor in a mutual embrace that becomes stronger under stress. The result is a resilience that has kept these walls standing for over 500 years in one of the most seismically active regions on the planet, a silent testament to the power of connection without constraint. Stone could dance and wood could sway, but the true came when these two materials learned to work as one. While the polygonal walls of the Inca showcased stone's strength through intricate connection, other ancient builders discovered a hybrid approach, embedding the flexibility of wood directly into the heart of seemingly rigid stone. This was not merely decoration, it was a hidden skeletal system, a timber framework locked inside masonry walls that gave entire structures a resilience modern concrete often struggles to match. The Romans were pioneers of this technique. Their famous concrete, a revolution in building, was often poured around a complex internal lattice of wooden beams. This grid, embedded within the thick walls of aqueducts, temples, and amphitheaters, served a critical dual purpose. First, it acted as a holding the wet concrete in shape as it cured. But long after the concrete had hardened, that wooden skeleton remained, now performing a vital seismic role. When an earthquake's tremors struck, the rigid concrete wanted to crack in brittle, catastrophic lines. The internal timber grid, however, possessed a quality concrete lacks: tensile strength. It could stretch and flex. As the concrete around it began to strain, this wooden network absorbed and redistributed those forces, holding the masonry together like an internal net, preventing localized cracks from becoming total failures. It was the ancient equivalent of the steel rebar we use today, a flexible reinforcement that gave a brittle material the gift of bend. This wisdom traveled along the Silk Roads and found profound expression in the architecture of the empire in India. Here, in regions frequently shaken by tremors, builders perfected the use of wooden tie beams, known as or. Look closely at the majestic walls of forts and tombs, like those in Rajasthan or at the Taj Mahal complex. And you will see horizontal bands of dark wood running through the red sandstone or marble like elegant stripes. These were not merely aesthetic accents, they were seismic belts. These wooden beams, integrated at regular intervals up the height of a wall, tied the entire structure together laterally. During an earthquake, while the stone sections might try to sway independently, these continuous wooden bands forced them to move as a single, coherent unit. They absorbed the shear forces, the sideways sliding motions that are so destructive to masonry, and distributed that energy evenly throughout the wall's height. Think of it as a stack of books. If you push the top book, it will easily slide off. But if you drill a rod vertically through the entire stack, binding them together, they move as one solid block and are far harder to topple. These wooden tie beams performed that binding function, transforming a vulnerable pile of heavy stone into an integrated, flexible monolith. Perhaps the most sophisticated expression of this timber and stone symbiosis comes from ancient China, particularly in the construction of its monumental timber frame temples, which often sit upon massive stone platforms. The Chinese system took the concept of flexibility to a holistic level. The entire weight of the heavy tiled roof was supported not by walls, but by an intricate, self-supporting wooden skeleton of columns, beams, and brackets, known as. The walls themselves were often load-bearing, acting more like curtains that could fill the spaces between columns. This was a seismic revelation. When the ground shook, the rigid stone platform could move, and the flexible wooden frame above could sway and rock on its own, with the lightweight infill walls offering little resistance. The complex bracket systems, consisting of interlocking wooden blocks and arms, acted as sophisticated shock absorbers, their joints allowing for compression and rotation, dissipating energy through friction and minute movements. This design philosophy, perfected over 1,000 years, created structures that could undergo dramatic deformation without collapse, a principle known as ductility. The building was engineered to bend so it would not break, and the careful integration of a heavy, stable base with a light, flexible superstructure was key. It shows a profound understanding that different materials have different roles to play in the dance of survival, with stone providing grounded mass and wood providing life-giving flex. This ancient collaboration between timber and masonry whispers a crucial lesson, that sometimes the strongest defense is not a single, perfect material, but a clever partnership where each component's weakness is guarded by the other's strength. But the most profound innovations were not always hidden in the walls. Sometimes they were carved into the very earth itself. In the dense Cambodian jungle, the temple complex of Angkor Wat presents a different kind of seismic wisdom, one that addresses a threat modern cities still fear: liquefaction. Built upon a foundation of loose, sandy soil, this sprawling stone city should have been a prime candidate for catastrophic sinking during the region's frequent tremors. Yet it stands, a testament to an ingenious environmental solution that turned the landscape into a stabilizing force. The builders did not just construct a temple, they engineered an entire hydrological system. The most visible feature is the enormous, rectangular moat that surrounds the central complex, a massive trench over 600 feet wide, filled with water. For centuries, it was seen primarily as a symbolic representation of the cosmic ocean and a formidable defensive barrier. But modern geological research suggests its most vital role was far more practical. It acted as a giant, permanent reservoir that maintained a consistently high water table beneath the temple grounds. This constant saturation was the key to survival. Dry, loose sand is a treacherous foundation during an earthquake. The violent shaking can cause the grains to lose contact with each other, turning the solid ground into a temporary, viscous fluid that can swallow buildings whole. This is liquefaction, a phenomenon that has toppled countless modern structures. By keeping the sand perpetually wet, the Angkor builders fundamentally changed its physical behavior. The water pressure between the grains helped lock them together, increasing friction and giving the substrate a cohesive strength. When seismic waves passed through, the saturated sand was far less likely to fluidize. It behaved more like a damp than dry, shifting dunes. The moat was not just a trench, it was a monumental stabilization project, a giant weight and water source that pinned the landscape in place. It ensured the ground beneath those impossibly heavy stone towers remained a solid platform, not a liquid trap. This reveals a breathtaking scale of foresight, where the builders understood that to protect a structure, you must first protect the earth it stands upon. They saw the temple not as an isolated object, but as the peak of a carefully managed ecosystem, where every element, from the grandest tower to the water in the ditch, worked in concert to defy the chaos below. This brings us to a final, humbling question. What if the very glue holding these ancient wonders together was itself a secret weapon? We assume modern concrete is the pinnacle of strength, a rigid, uniform substance that locks stone in place forever. But history reveals a different truth. Some of the most enduring mortars were not designed to be unbreakable, but to be alive. The Romans, for instance, did not use the simple lime mortars common in later centuries. Their concrete was a sophisticated recipe, a mix of lime, water, and a crucial ingredient, volcanic ash from a region called. This ash, known as pozzolana, reacted chemically with the lime and water to form a crystalline binder that was incredibly durable, yes, but also possessed a miraculous quality, flexibility. Unlike modern Portland cement, which cures into a hard, brittle matrix that cracks under stress, Roman concrete remained slightly more plastic. It could accommodate subtle shifts and movements within a wall without failing catastrophically. Even more astonishing, it had a self-healing property. When tiny cracks did form from seismic stress or simple settling, moisture would seep into these fissures. This water would react with unused pozzolana particles in the concrete, triggering the formation of new calcium silicate crystals. These crystals would slowly grow, filling the crack from the inside out, essentially healing the wound. The material literally repaired itself over time, a built-in maintenance system operating on a geological timescale. This was not a brittle adhesive, it was a dynamic, responsive part of the structure's ecosystem. Similarly, many ancient lime mortars used in temples across the world, from India to, were engineered for resilience. They were often mixed with organic additives like rice husks, fruit juices, or even curd, which created a more fibrous, breathable matrix. This allowed the mortar to flex and absorb movement, and its porous nature permitted moisture to evaporate rather than get trapped and caused the stone to spall or crack during freeze-thaw cycles. The goal was never to create a permanent, rigid weld, but a forgiving, adaptable joint that worked in partnership with the stone. It is a profound shift in perspective. We build for immediate, absolute strength. They built for longevity through forgiveness. Their materials were not inert. They were participants in the structure's life, designed to yield, to heal, and to endure alongside the stones they bonded. In the quiet chemistry of their mortar, we find the same principle that guided their columns and timber frames. True endurance is not about refusing to break, but about possessing the innate ability to mend. These subtle curves and bulges were far more than an artistic whim. Look closely at a classical Greek column, and you will notice it is not a perfect cylinder. It swells gently in the middle, tapering ever so slightly toward the top. This intentional imperfection has a name, Entasis. For centuries, art historians viewed it as an optical correction, a clever trick to make the column appear straight and powerful to the human eye from a distance. While that visual effect is real, there is a compelling argument that its greatest purpose was not to please the eye, but to strengthen the stone against the earth's tremors. A perfectly straight column under immense vertical load is vulnerable. Its stress is distributed evenly but uniformly. When a horizontal force, like an earthquake shake, strikes it, that force meets a rigid, unbending form. Entasis changes the geometry of the fight. By thickening the column at its midpoint, where bending stress is greatest, the builders effectively reinforced its most vulnerable section. Think of a tree trunk in a strong wind. It is thickest at the base and tapers as it rises, a natural design for handling lateral forces. Entasis mimics this organic wisdom. The bulge creates a more complex load path for seismic energy, allowing the column to flex and dissipate force through its curved profile, rather than concentrating it into a sharp, brittle failure line. It turns a simple post into a dynamic, shaped beam, better equipped to handle the push and pull of a trembling world. This was precision engineering disguised as beauty, a calculated deviation from perfection that made the structure as a whole more perfect for its environment. This philosophy of deliberate imperfection extended beyond individual columns to the entire layout of sacred spaces. Some of the most revered temples, upon precise measurement, reveal they are not the perfectly symmetrical rectangles we imagine. Subtle asymmetries exist, offsets in the placement of columns or variations in the spacing between them. For a culture capable of breathtaking precision, these were not errors. They were likely intelligent adaptations. A perfectly symmetrical building, while pleasing to our sense of order, can have a uniform and potentially resonant response to vibration. Like a tuning fork, it might vibrate in a predictable, amplified way. By introducing controlled irregularities, the builders may have been detuning the structure. These slight variations in mass and spacing would break up the rhythmic transfer of seismic waves, preventing the building from rocking in a single, synchronized, and destructive frequency. Instead, different sections would move slightly out of phase with each other, their motions canceling one another out, dampening the overall oscillation. It is the architectural equivalent of a choir singing in harmony rather than a single voice shouting one loud note. The combined effect is richer, more complex, and far more stable. This suggests the ancients understood their buildings not as static sculptures, but as dynamic instruments interacting with the forces of nature. The goal was not rigid, flawless symmetry, but a living, balanced resilience. In these quiet deviations from the blueprint, we see a humility before natural law, an acknowledgement that to achieve enduring harmony with a chaotic earth, one must sometimes build a little discord into the plan. The pyramid shape represents a different kind of answer to the earthquake's challenge. From the sands of Giza to the jungles of Central America, this iconic form stands as a monument to pure, geometric stability. Unlike the dynamic, dancing structures we have explored, the pyramid's genius lies in its profound stillness. Its seismic resistance is not about flexibility, but about presenting the Earth with a problem it cannot easily solve. The design principles are beautifully simple and devastatingly effective. First, its wide base provides an enormous footprint, spreading its incredible weight over a vast area of ground. This minimizes the pressure on any single point of the foundation, preventing sinking or tilting even if the soil beneath it shifts. Second, its sloping or stepped sides create a low, central center of gravity. Imagine trying to topple a child's wide base toy. You have to push it very far before it tips over. A pyramid is that toy on a monumental scale. All of its mass is concentrated downward and inward, making it incredibly resistant to being rocked off its base by horizontal shaking. It wants to stay put. Finally, the shape itself defeats a key agent of destruction, resonant frequency. Tall, slender buildings can act like tuning forks, their natural vibration rhythm matching and amplifying the frequency of certain earthquake waves, leading to catastrophic oscillation. A pyramid with its massive base and tapering form has no single, dominant frequency. The seismic waves traveling up through it are scattered and dissipated by its changing geometry, their energy fading before it can organize into a coherent, destructive force. The pyramid is, in essence, a seismic dampener carved in stone. It survives not by dancing with the quake, but by being an immovable, inert mountain. It is the ultimate expression of passive resistance, a lesson that sometimes the most powerful response to chaos is not movement, but an unshakable, monumental calm. But to see these temples only as feats of engineering is to miss half the story. Their construction was not a purely technical act. It was a sacred dialogue, where every stone laid was a prayer and every measurement a ritual. The meticulous practices we admire for their precision were often inseparable from spiritual ceremonies, creating a fusion of faith and physics that yielded profoundly practical results. Consider the cornerstone ceremony, a tradition found in countless cultures from ancient Mesopotamia to medieval Europe. Before a single wall was raised, the community would gather for a solemn ritual to lay the first stone. Priests would chant, offerings would be made, and the stone would be blessed. On the surface, this was an act of dedication, inviting divine protection for the building and those who would use it. But look closer, and you see a brilliant practical strategy embedded within the sacred theater. This ceremony forced a pause, a deliberate and extended focus on the absolute foundation of everything to come. It ensured that this first, critical stone was set with obsessive care, perfectly level and aligned, because the entire geometric truth of the temple would flow from this one point. A rushed or misaligned cornerstone would doom the entire structure to a cascade of errors. The ritual created a cultural imperative for perfection at the most vulnerable moment of construction. It turned a technical task into a communal vow, guaranteeing the attention it desperately needed. Similarly, many cultures observed prolonged ceremonies for the preparation of the building site itself. There are accounts of grounds being consecrated and then left untouched for an entire season, or of repeated rituals involving water libations over many days. From a spiritual perspective, this was about purifying the land, allowing it to rest, or letting it absorb blessings. From a geotechnical perspective, this waiting period was a gift. It allowed for soil consolidation. When you excavate a foundation trench, you disturb the earth, creating loose, unstable layers. If you build immediately on this unsettled ground, the weight of the structure will cause it to compact unevenly over time, leading to cracks and tilts. But if you allow a season of rains and natural settling, perhaps aided by ritualistic soaking, the soil particles rearrange themselves into a denser, more stable configuration. The ground essentially heals itself before the load is applied. What was recorded as a time of prayer and purification was also, unknowingly, a critical phase of geotechnical stabilization. The ritual enforced the patience that the earth demanded. This intertwining extended to the very materials. The act of quarrying stone was often governed by strict rites. Certain times of the year, like specific lunar phases, were deemed auspicious for cutting stone from the living earth. This likely coordinated labor with optimal weather conditions, avoiding the brittle cold of winter or the torrential rains of monsoon season that could make quarrying dangerous and transport impossible. The blessing of tools was not just about safeguarding the craftsman. It was about instilling a mindset of reverence for the material, encouraging careful, deliberate work that reduced waste and improved the quality of each block. When a community believed the spirit of a mountain resided in its stone, they handled that stone with a care that went beyond mere utility. This cultural mindset directly resulted in the finer joints, the more precise carving, and the overall superior craftsmanship that gave these temples their legendary durability. The ritual created the conditions for excellence. It was a system where belief did not replace engineering. It enforced the highest standards of it, wrapping hard necessity in a story that gave every participant a sacred role in the creation of something eternal. The temple's resilience was born not just from the mind of the architect, but from the collective heart of the community, proving that sometimes the most enduring foundations are those laid with both a plumb line and a prayer. This deep integration of ritual and craft points to a final, haunting mystery. How was this sophisticated seismic knowledge, this intuitive physics, preserved and transmitted across centuries without a single textbook or engineering degree? The answer lies not in libraries, but in the living chain of human experience. In a world before formal science, the laboratory was the trembling earth itself, and the data was written in the ruins of failures and the enduring grace of successes. The master builders of antiquity operated within a powerful system of knowledge transfer, one that was slow, meticulous, and encoded directly into the work. At its heart was the master-apprentice relationship, a decades-long immersion that went far beyond teaching how to lay a stone. A young apprentice would not just learn to carve, he would absorb an entire philosophy of building through relentless observation and repetition. He would hear the stories of the great quake of his grandfather's time, the one that toppled the old temple on the hill. He would feel with his own hands the subtle swell of Entasis on a column drum his master was shaping, and learn that this curve was not optional, it was essential. He would mix mortar according to a recipe passed down like a family secret, learning the exact feel of the right consistency, a knowledge carried in the muscles and the senses. This was tacit knowledge, wisdom that lived in the body and the intuition, transferred through shared labor and silent understanding. It was a continuous, unbroken conversation between generations, where each master added his own hard-won insights to the collective memory before passing the tools to the next set of careful hands. This living knowledge was also crystallized into more tangible forms, the proportional systems and design templates that governed sacred architecture across cultures. The Greek orders Doric, Ionic, Corinthian were not just aesthetic styles, they were complete rulebooks for construction. Every dimension, from the height of a column to the depth of its fluting, was defined as a multiple of a base unit, often the diameter of the column's base. This modular system ensured harmony and balance, but it also encoded seismic resilience. Once a community, through trial and painful error, discovered a set of proportions that produced a stable, dancing temple in their particular landscape, they locked that successful recipe into a cultural standard. A builder in a new city didn't need to understand the complex physics of shear forces. He simply needed to follow the sacred proportions of the Doric order, and the earthquake-resistant qualities were baked into the geometry. The template carried the wisdom forward. We see this same principle in the Shastra of India, or the principles of China, intricate systems that dictated everything from site orientation to room dimensions. While framed as spiritual directives to align with cosmic energies, they functionally produced buildings with specific, often beneficial, structural relationships. Like cross-ventilation for cooling or strategic placement of heavy masses for stability. The rulebook itself became the vessel for survival knowledge, a way to transmit a complex environmental adaptation in the guise of divine law. Each generation built according to the code, and in doing so, they preserved and reinforced the invisible engineering within it. This process was not static. It was a slow, generational algorithm of trial and error. A community would build a temple. Perhaps a tremor would come and cause a crack in a new, experimental arch design. That failure was a critical data point. The next generation, repairing the damage, would adjust the design, perhaps thickening the arch or changing the angle of the stones. If the new solution held, it became part of the local canon. Success was not celebrated as a breakthrough in seismic theory, but simply as the right way to build, the way that pleased the gods and kept the roof standing. Over centuries, these incremental, almost imperceptible refinements, each one tested against the brutal reality of the Earth's movements, led to the extraordinarily refined structures we marvel at today. The perfect curve of a pagodas, the precise angle of an Inca stone joint, these were not sudden inventions. They were the polished result of countless minor corrections, a dialogue with disaster conducted over hundreds of years. The knowledge survived because it was not abstract theory. It was practical, proven, and woven into the very identity of the builders and the spiritual life of the community. It was a wisdom written not on parchment, but in stone, and taught not with lectures, but with the steady rhythm of the mallet and chisel, a rhythm that echoed the patient, teaching heartbeat of the earth itself. Yet this ancient wisdom was not always heeded, and history holds quiet lessons in the consequences of forgetting. For every temple that danced and survived, there are sites where later generations, with the best of intentions, introduced a fatal rigidity. These counterexamples are not failures of the original vision, but proof of it, revealing what happens when a flexible system is locked down. In many cases, the very repairs meant to save a structure ultimately sealed its fate. Consider the fate of some classical temples in the Mediterranean. Centuries after their construction, Roman engineers or later medieval builders would encounter cracks in the elegant stonework, the natural settling and seismic scars of age. Their solution was often to pour new, stronger mortar into the joints, or even to insert rigid iron clamps to hold stones together. On the surface, this made perfect sense, to bind the wound and make it solid. But it fundamentally misunderstood the building's original logic. Those flexible joints, those lead cushion connections, were designed to be the shock absorbers. By filling them with hard cement or clamping them with unyielding iron, the repairers eliminated the structure's ability to sway and dissipate energy. They turned a dynamic, living framework into a brittle cage. When the next major earthquake struck, the forces that once flowed harmlessly through countless micro-movements now had nowhere to go. The energy concentrated at the newly rigid points, and the structure, unable to flex, would shatter along new, catastrophic lines. The repair, meant to reinforce, had instead made the building profoundly vulnerable. It is a poignant reminder that strength and stiffness are not the same thing, and that a fix born from a different philosophy can break a system perfectly tuned to its environment. This pattern repeats in astonishing ways across different cultures. In some regions of Asia, ancient pagodas or temples that had survived for centuries faced a similar intervention. As religious practices evolved, communities sometimes sought to make their sacred structures grander, more imposing symbols of faith. They would add heavier tile roofs, construct massive additional tiers, or encase delicate wooden frames in thick layers of plaster and brick. Each addition was a gesture of devotion and prosperity. But each one also added dead weight high above the ground, raising the center of gravity and increasing the inertial forces during a quake. The original lightweight, flexible design, balanced like a reed, was now burdened with a load it was never meant to carry. The elegant dance of the suspended pillar, or the flexible timber frame, was overwhelmed by sheer mass. In a major tremor, these top-heavy modifications could cause the structure to rock too far, topple, or crush its own base. The very desire to monumentalize the sacred undermined the subtle engineering that had kept it safe through generations of lesser shakes. These were not acts of ignorance, but of different priorities, where symbolic power was valued over seismic wisdom. The ruins they sometimes left behind stand as silent testimonials to a trade-off, a moment where the tune of the building was changed, and it could no longer sing in harmony with the moving earth. These stories of modification and collapse bring us to a crucial and humbling realization. The original builders were not just stacking stones, they were tuning instruments. Each proportion, each material choice, each flexible joint was part of a complex system calibrated to the specific frequencies and forces of their local landscape. A temple in Greece was tuned to the shudder of the Aegean basin. A pagoda in Japan was tuned to the deep, rolling waves of a Pacific subduction quake. Their resilience was not a generic recipe, but a local adaptation, refined over generations of silent observation and incremental adjustment. When later builders came with new materials and new intentions, they often applied a one-size-fits-all logic of rigid reinforcement. They saw a crack and sought to weld it shut, not understanding that the crack was part of the language, a way for the building to speak its stress and release it. In doing so, they deafened the structure to the Earth's movements. This historical pattern mirrors a challenge we still face today. Our modern engineering is brilliant, but it often relies on universal codes and standardized materials. The ancient approach whispers that true resilience might be deeply contextual, requiring us to listen to the specific song of the land before we try to build a chorus upon it. The collapse of these modified structures is not a tale of ancient inferiority, but a demonstration of just how precise and delicate their original equilibrium truly was. It shows that their survival was never an accident, but the product of a profound and specific harmony, one that could be broken by the simple, well-meaning act of trying to make it stronger. The dialogue with disaster did not end with the classical world. As empires rose and fell, the relentless tremors of the Mediterranean and Near East continued to teach their harsh lessons, forcing builders to innovate once more. In the seismic heartlands of the Byzantine and Armenian worlds, a new architectural language emerged. One that refined the ancient principles of flexibility into forms of breathtaking grace and formidable strength. Here, the challenge was the dome, a magnificent but perilous feature. A traditional hemispherical dome exerts tremendous outward thrust on the walls that support it, a constant, silent pressure. In an earthquake, that pressure becomes a violent, rocking force that can easily push walls apart and bring the entire roof crashing down. The solution was not to abandon the dome, but to reinvent its relationship with the building beneath it. Byzantine architects, particularly in regions like modern-day Turkey and Greece, developed of structural thinking, the transition from a square base to a circular dome. Instead of simply setting a round dome on top of 4 flat walls and hoping for the best, they introduced an ingenious intermediary element, the squinch. A squinch is essentially a small arch or series of stepped arches built across the interior corners of a square room. These arches bridge the gap, gradually converting the square at the top of the walls into an octagon, and then into a circle, creating a smooth, graduated platform for the dome to rest upon. This was far more than a decorative trick. It created a continuous, flowing load path. The weight and thrust of the dome were now channeled down through these arch transitions and into the main piers at the corners of the building, the strongest points. The stress was directed, not concentrated. The squinch acted as a shock absorber, a built-in flexibility that allowed the different geometries of the square base and round dome to move together during a tremor without creating a catastrophic shear line where they met. It was a formalization of the ancient idea of distributing force, now engineered into the very shape of the sanctuary. But the innovations did not stop at the interior. Looking at the skyline of an ancient Byzantine church, you will often see a forest of external arches and buttresses clinging to its walls. These are not later additions. They were part of the original design, a kind of external skeletal system. Known as reinforcing arches or flying buttresses in their earlier forms, these structures served a clear seismic purpose. They tied the building together laterally, creating a rigid external frame that counteracted the dome's outward push. During an earthquake, while the main walls might want to sway independently, these external arches forced them to move as a single, braced unit. They absorbed the lateral shaking and transferred those forces down into the ground through their own foundations, effectively giving the church an exoskeleton. This was a move from an internalized flexibility to a system of integrated external reinforcement, a visible acknowledgement of the constant battle with the earth. Perhaps the most distinctive adaptation, however, is seen in the majestic stone churches of medieval Armenia, a region crisscrossed by fault lines. Here, architects developed a signature silhouette, the conical dome. Unlike a shallow, hemispherical dome, the Armenian dome rises to a steep, pointed peak, often sheathed in a conical or polygonal roof. This shape is profoundly seismic. The steep pitch naturally sheds weight downward more efficiently, reducing the horizontal thrust on the supporting walls. More importantly, the tall, conical form is inherently more stable against rocking. Its geometry makes it act like a gyroscope, resisting the toppling forces of a quake. The entire structure, from its massive stone walls to its soaring central tower, was conceived as a monolithic tapered mass, a mountain carved by human hands. The builders further enhanced this stability by using lightweight, porous stone for the upper sections of the dome, lowering the center of gravity. Every choice, from the grand silhouette down to the selection of materials, was a calculated response to a treacherous ground. These medieval adaptations represent a fascinating evolution. They took the intuitive principles of flexibility and distribution observed by earlier civilizations and them into specific, repeatable architectural features. The squinch systematized load transfer. The external arch provided measurable reinforcement. The conical dome optimized form for stability. This was no longer just the wisdom of the master carpenter or stonemason. It was becoming a formalized architectural science. A direct and eloquent response, written in stone, to the enduring question of how to build for the sky in a world that constantly threatens to shake you back to earth. But the most resilient dance between earth and architecture often began where no one could see it, deep below the surface in a hidden world of preparation. While we marvel at soaring columns and intricate domes, the true secret to a temple's longevity was frequently buried, a forgotten middle layer of ingenious subterranean engineering. Ancient builders understood that a structure is only as stable as what lies beneath it, and they dedicated immense effort to creating foundations that were not just solid, but smart. Instead of simply placing massive stone blocks directly on the excavated earth, they constructed complex, layered platforms designed to manage both weight and water. A common technique involved creating a foundation pad composed of alternating materials. They might start with a bed of compacted clay, then add a layer of flat stones set in mortar, followed by a thick stratum of loose rubble and gravel, and then another layer of stone. This sandwich was deliberate physics. The rigid stone layers distributed the immense weight of the walls above, while the intermediate layers of clay and rubble acted as internal shock absorbers. During an earthquake, the different materials would move and settle at slightly different rates, the rubble grinding and shifting within its layer. This internal friction dissipated seismic energy before it could travel cleanly and destructively up into the temple's visible walls. It was like placing the entire building on a giant, engineered mattress that could absorb the worst of the tremors. But managing shaking was only half the battle. Water was, and remains, a foundation's silent enemy. Pooling water can erode soil, cause frost heave in cold climates, and promote rot in wooden elements. Here, another brilliant low-tech solution emerged, the rubble trench. Before laying any foundation stones, builders would dig a trench wider than the planned walls and fill it with a deep bed of loose stone, broken pottery, and gravel. This trench served as a French drain long before the term existed. Its primary function was hydrological, to create a capillary break. When rainwater permeated the soil around the foundation, it would hit this layer of large, air-filled voids in the rubble trench. Instead of continuing upward into the foundation masonry where it could cause damage, the water would quickly drain down and away through the path of least resistance. This kept the actual foundation stones and the soil directly beneath them relatively dry and stable. A dry foundation is a happy foundation, far less susceptible to settling, shifting, or the destructive freeze-thaw cycle. Furthermore, this loose, drainable fill also provided a degree of seismic resilience. Unlike solid, water-logged earth that could liquefy, the gravel-filled trench remained free-draining and cohesive, less likely to turn into a fluid under pressure. It was a multi-purpose innovation, solving the twin problems of drainage and stability with one elegant, buried design. These subterranean strategies reveal a profound humility and foresight. The builders knew that the glory of the temple, the part meant to inspire awe and reach for the heavens, depended entirely on this unseen, unglamorous work below. They invested labor and material into layers no one would ever see, because they understood that true endurance is built from the ground up, beginning with a respectful conversation with the very earth they sought to rise above. South India offers in this principle of distributed strength, written in stone on a monumental scale. Here, the approach to seismic survival is not hidden in subtle curves or buried foundations, but proudly displayed in the most iconic feature of the temple complex, the soaring. These are the colossal, pyramid-shaped gateway towers, often covered in a breathtaking tapestry of carved deities and mythical figures that mark the entrance to sacred precincts. To stand at the base of one is to feel dwarfed, not just by its height, which can reach over 200 feet, but by its apparent defiance of physics. How can such an ornate, top-heavy stone giant possibly withstand the region's powerful tremors? The answer is a brilliant lesson in structural hierarchy and intelligent decomposition. The is not built as a single, monolithic tower. It is constructed as a series of distinct, stacked stories, each one slightly smaller than the one below it, creating that iconic steep pyramidal profile. This is far more than an aesthetic choice. It is a seismic strategy. Each story is designed to function as an independent structural unit. They are not rigidly locked together, but are built with a degree of autonomy. During an earthquake, these stacked masses can rock and sway somewhat independently of each other. The movement of one story does not directly force the same movement onto the story above. Instead, the energy is dissipated at each level as the stones grind and settle at their joints. This prevents the entire tower from developing a single, synchronized, and destructive swaying motion. It is like a stack of books where each book is allowed to slide a tiny amount on the one below it. The whole stack can absorb a lateral push without toppling over. But the real engineering marvel lies within the walls themselves. These towers are not solid stone that would be far too heavy and brittle. Instead, they are built as a massive stone shell using a technique called corbelling. Imagine building an arch, but instead of using wedge-shaped keystone at the top, you lay each stone so it projects slightly inward over the one below it. Continue this process from opposite walls, and eventually the projecting stones meet in the middle, closing the gap and forming a corbelled arch or roof. The builders of the used this principle to construct the entire internal structure. The walls are essentially two parallel stone skins, with the space between them filled by a complex lattice of interlocking corbelled stone brackets. This creates a honeycomb-like interior, a three-dimensional web of stone that is incredibly strong for its weight. This honeycomb structure is a masterpiece of efficient force distribution. When a seismic wave hits the tower, the energy travels through this internal lattice. The honeycomb design, with its countless small chambers and interconnections, forces the energy to split and travel along myriad tiny paths. The force is scattered and dissipated as friction within the labyrinth, rather than being channeled into a few catastrophic fault lines. It is the architectural equivalent of a crumple zone in a modern car, a sacrificial, complex structure designed to absorb and disperse impact energy in a controlled way, protecting the overall form. Furthermore, the corbelled joints themselves have a hidden flexibility. Because each stone is simply resting on the one below it, held in place by gravity and friction, they have a minute capacity to shift and adjust under stress. They are a system of dry stone masonry on a colossal scale, inheriting the same seismic wisdom seen in Inca walls. The towering, ornate, therefore, stands not as a fragile monument to ambition, but as a resilient, layered system. Its pyramidal shape lowers the center of gravity, its stacked stories act as independent dampers, and its honeycombed heart scatters destructive energy into harmless friction. It is a testament to the idea that true stability in a dynamic world comes not from rigid unity, but from a harmonious assembly of resilient, semi-independent parts. The relentless forces of nature rarely arrive alone. In the coastal and island regions of Southeast Asia, ancient builders faced a dual threat: the terrifying horizontal fury of earthquakes and the immense lateral pressure of typhoon winds. These are two very different phenomena, one rising from deep within the earth, the other screaming across its surface. Yet remarkably, the architectural solutions developed to withstand one often provided a powerful, if unintentional, defense against the other. This reveals a fascinating principle of resilient design. Sometimes the best answer to a complex challenge is an elegant, multi-purpose form. The region's iconic temple architecture, from the wooden miao of southern China to the stilted structures across the archipelago, evolved features that managed both sky-born and earth-born chaos with a single brilliant strategy. The most visible of these is the profoundly deep, overhanging roof. These roofs, often layered in multiple sweeping tiers, are a direct response to the monsoon climate and typhoon winds. Their primary job is practical: to throw rainwater far away from the vulnerable wooden walls and foundation, protecting the structure from rot and erosion. But that dramatic overhang does something else. It adds significant mass relatively low on the building's profile. While the roof is high, its heaviest part, the thick tiles and supporting beams, is pushed outward, not upward. This effectively lowers the structure's center of gravity, making it less top-heavy and far more resistant to being rocked over by lateral forces, whether from wind or seismic waves. It is the same principle as a toy. The weight at the bottom keeps it upright. Furthermore, these large roofs were typically supported not by the walls, but by an independent, flexible timber frame, much like the pagodas of Japan. This meant the heavy roof could sway and rock on its own skeletal system during a tremor, its inertia acting as a stabilizing pendulum mass, while the walls beneath, freed from carrying the load, could also move without immediate collapse. The roof became both a protector from rain and a seismic counterweight. This wisdom extends to the very foundation of life in these regions, the raised floor. In flood-prone and vermin-rich environments, elevating a living or sacred space on wooden or stone pillars is a straightforward health and safety measure. But this elevation also creates a critical seismic buffer. The structure is decoupled from the direct, jarring movements of the ground. When an earthquake's waves roll through, they move the pillars first. These pillars, made of wood, have a natural flex. They can bend and sway, absorbing and dissipating energy before it fully transfers into the main living area above. The raised floor essentially places the precious human space on a platform of natural shock absorbers. It is a form of base isolation using organic materials, turning a necessity of climate into a virtue of seismic safety. This confluence of solutions points to a deeper truth about vernacular architecture. It is born from a holistic response to the environment. The builders were not solving for earthquakes or typhoons in isolation. They were solving for survival in a specific, demanding place. The forms that emerged, shaped by generations of trial and error against all the forces their world could muster, naturally embodied principles of low centers of gravity, flexible connections, and decoupled masses. They did not need a textbook on lateral loads to understand that a building that could dance with the wind would also fare better when the earth began to move. In their pragmatic adaptations to the daily and seasonal challenges of their climate, they inadvertently engineered an in-hazard resilience, proving that the most enduring designs are often those that listen to every whisper and shout of the natural world. For centuries, this ancient dialogue with the trembling earth was preserved only in stone and story, a kind of silent, practical wisdom. Then, in the 20th century, something remarkable happened. A new generation of engineers and seismologists, armed with instruments and equations, began to look back. They were not searching for mysticism, but for data. Their laboratories were the ruins of failed buildings and the enduring frames of survivors. As they meticulously mapped the damage patterns from modern earthquakes, a recurring question emerged: why did some old structures, built with what seemed like primitive methods, often fare better than their modern, reinforced counterparts? This inquiry sparked a quiet revolution, a scientific journey to reverse engineer the past. The goal was no longer to dismiss ancient methods as lucky accidents, but to decode their hidden physics. When researchers modeled the rocking of stacked stone columns or analyzed the sway of a pagoda's suspended pillar, they found not chaos, but elegant, predictable systems of energy management. They gave scientific names to the principles these builders had intuitively grasped. Ductility, the ability of a material or system to deform under stress without breaking, was no longer just a property of steel. It was the exact behavior observed in those flexible timber frames and forgiving mortars. Energy dissipation, the crucial process of converting destructive seismic force into harmless heat or motion, was precisely what happened inside the honeycombed walls of or across the grinding joints of polygonal masonry. The ancient world had mastered passive damping systems long before the term existed. This validation was profound. It meant the intuitive rules passed from master to apprentice were not superstitions, but a form of proto-science, a deep empirical understanding of how materials interact with forces. The modern engineer, with a slide rule and a seismograph, was finally learning to speak the language that the stonemason had known in his hands. This bridge between eras did more than just satisfy historical curiosity. It began to directly influence how we build for the future. The principles of base isolation, now implemented with high-tech rubber bearings, echo the floating foundations of Japanese pagodas. The ductile detailing in our steel frames seeks to replicate the controlled, graceful yielding of a timber bracket. We are, in essence, rediscovering a timeless truth that resilience is not about brute force against nature, but about intelligent cooperation with it. The ancient temples were not just buildings, they were long-term experiments, and their continued survival is the data point that modern science can no longer ignore. The rediscovery of these ancient principles did not remain a historical footnote. It sparked a tangible revolution in how we protect our own cities from the very same forces. That simple, profound idea of a floating foundation, observed in pagodas resting on stones, became the seed for one of the most important seismic innovations of the modern era: base isolation. Today, this ancient concept is engineered into the literal bedrock of critical infrastructure worldwide. Instead of rounded stones, we now use sophisticated devices called elastomeric bearings. These are massive, layered sandwiches of steel plates and thick rubber pads, installed between a building's foundation and the ground. During an earthquake, the ground lurches violently, but these rubber bearings flex and deform, allowing the entire building above to slide horizontally, slowly and smoothly, like a ship floating on a cushion of water. The structure is decoupled from the worst of the shaking, its inertia keeping it relatively still while the earth moves beneath it. It is the exact same principle of detachment, now executed with polymer chemistry and precision manufacturing. You will find these systems protecting hospitals, fire stations, data centers, and museums from San Francisco to Tokyo, ensuring that life-saving services and cultural treasures remain operational after a major tremor. The goal is identical to the ancient builder's intuition: to let the foundation absorb the chaos so the building does not have to. We even see variations like sliding plates, where a building sits on smooth, lubricated surfaces that allow it to shift, again mirroring that ancient wisdom of permitting movement. This is not merely a coincidence of design, it is a direct lineage of thought. Modern engineers, confronted with the limitations of rigid resistance, looked back and saw in those ancient survivors a validated alternative. They translated an empirical observation into a calculable science, proving that the old way was not primitive, but profoundly prescient. The silent dance of the pagoda on its stones now guides the calibrated sway of a skyscraper on its rubber pads, a testament to the timeless truth that sometimes the safest place to be during a storm is not anchored to the deck, but floating freely above the waves. Yet for all their genius, these builders were not modern scientists in disguise. Their knowledge was rooted in a different kind of wisdom, one built from the ground up through relentless observation and the hard lessons of failure. They knew what worked, often with astonishing precision, but they did not possess the theoretical framework to explain precisely why. A master stonemason in Greece could feel the perfect convex curve of a column drum and know it made the temple stand longer. He learned this not from a formula for stress distribution, but from seeing the cracked ruins of older columns after a tremor. His knowledge was empirical, written in the language of cause and effect, not physics. He understood that a thicker layer of river gravel in the foundation trench led to less settling in the walls after the rainy season. He did not call it improved drainage or soil compaction. He simply knew it as the right way passed down from his teacher. This distinction is crucial. It tempers our admiration with historical accuracy. These were not engineers calculating load paths and resonant frequencies. They were brilliant artisans and observers whose rules of thumb were forged in the unforgiving laboratory of a seismic landscape. Their codes of proportion, their ritualized construction sequences, even their material recipes, were containers for this hard-won, practical knowledge. They encoded survival strategies into culture and tradition, ensuring the next generation built the successful way without needing to rediscover the principles through catastrophic collapse. This separation of proven technique from theoretical understanding does not diminish their achievement, it reframes it. It means their solutions were often optimized for their specific environment, and materials through a slow, generational process of elimination. A temple design that survived in Japan might not have worked in Peru, not because the builders were less clever, but because their empirical database was hyper-local. They were tuning their instruments to one specific song of the earth. This grounded, localized wisdom is perhaps their greatest legacy, a reminder that true resilience often comes not from universal theory, but from a deep, patient, and humble conversation with the place you call home. This empirical knowledge can now be tested in a virtual laboratory. Today, digital archaeology allows us to run experiments that would be impossible in the real world, using a tool called finite element analysis. Engineers and historians begin by creating an exquisitely detailed digital twin of an ancient temple, scanning every stone, joint, and imperfection with lasers. This is not a simple picture. It is a complex mathematical model where each virtual stone is assigned the precise physical properties of real marble or granite, its weight, density, and stiffness. Then, with the click of a button, researchers can subject this digital temple to the simulated forces of history's worst earthquakes. They can watch in slow motion as seismic waves from a long-forgotten tremor wash through the foundation and up the columns. This is where ancient intuition meets modern proof. For decades, scholars hypothesized that the Parthenon's stacked columns were designed to rock. The finite element model provides quantitative, undeniable evidence. As the digital quake hits, the simulation shows stress concentrations, visualized as glowing red hotspots of pressure, building at the rigid connections of a hypothetical monolithic column, predicting a swift, clean fracture. But when the model activates the actual, jointed design with its lead cushions, the result is dramatically different. Those red hotspots vanish, dissipating into a cool, blue-green aura of distributed energy. The individual stone drums can be seen rocking minutely, each one pivoting a few millimeters, grinding against its neighbor. The software calculates the exact amount of energy converted into harmless heat and sound through this friction, a number that confirms the system's stunning efficiency. This virtual experiment provides a clear answer. The rocking column system can reduce the peak stress on the structure by a significant margin, often by 30% or more. A difference between survival and collapse. It transforms a compelling theory into a validated engineering principle, giving us graphs and data to support what the ruins have whispered for. We are no longer just admiring their longevity, we are measuring it. This digital proof creates a profound responsibility for those tasked with preserving these ancient survivors. The very act of conservation now carries a seismic risk, a delicate choice between freezing a monument in time and allowing it to continue its ancient dance. Modern restoration often defaults to strength, using steel rebar and rigid epoxy to lock crumbling stones back into place. Yet this approach, while well-intentioned, can be a death sentence for a structure designed to move. Imagine replacing the original, lead-cushioned iron clamps in a Greek temple with stainless steel rods set in modern concrete. The repair looks solid, permanent. But the next time the earth shakes, that rigid new joint becomes a focal point for catastrophic stress, a place where the energy has nowhere to go but to shatter the ancient stone it was meant to save. The conservation becomes the point of failure, a tragic irony where the cure undermines the patient's own immune system. This has led to a growing philosophy in heritage science, known as soft or compatible restoration. The goal is not to make the structure as strong as possible, but to preserve its original behavior. This means meticulously studying and replicating the ancient materials and techniques. If a temple used a specific lime mortar mixed with crushed, conservators will analyze its composition and create a new mortar with similar flexibility, end. If wooden tie beams are decayed, they are replaced with new timber of the same species and grain orientation, connected with traditional joinery rather than steel plates. The aim is to maintain the ductility of the original system, to allow those carefully engineered micro-movements to continue. In some cases, this even means accepting a degree of controlled movement, monitoring cracks that open and close with the seasons or minor tremors, rather than sealing them shut with unyielding grout. It is a shift from seeing the monument as a broken object to be fixed, to understanding it as a living, breathing system in dialogue with its environment. The conservator's role becomes that of a facilitator, ensuring the temple can keep dancing to the old, proven rhythms, rather than forcing it to stand rigid and vulnerable. This philosophy recognizes that the greatest honor we can pay these master builders is not to overwrite their wisdom with our own, but to listen to the subtle language of their stones and preserve the delicate, life-saving flexibility they engineered so long ago. So, the digital models confirm the physics, and the soft restorations honor the original intent. Yet for every mystery solved, another seems to deepen, reminding us how much silent knowledge has slipped through the cracks of time. We are left with a gallery of breathtaking survivors, each posing its own quiet, stubborn question. Take the great hypostyle hall at Karnak in Egypt, a forest of 134 colossal stone columns packed tightly together. It has stood for over 3,000 years in a region not immune to tremors. Conventional seismic wisdom would argue this dense configuration is a liability, with columns so close they might pound against each other during a quake, yet they stand. Was there a hidden calculation in their spacing, a specific ratio between height and diameter and gap that allowed them to sway as a grove rather than as individual trees? Or was their sheer collective mass, acting as a single monolithic block, the simple brute force answer? We can model it, but the original builder's rationale remains a whisper in stone. Then there is the haunting case of techniques lost. We have decoded the rocking column and the floating pillar, but what about the recipes that have vanished? The Roman concrete that heals itself is a celebrated rediscovery, but how many other material sciences have faded? The mortars that bound the Cyclopean walls of Mycenae, or the specific blend of clays and fibers in Mesopotamian bricks that gave them unusual flexibility. These are formulas known only by their results. Each represents a full branch of practical knowledge, developed over generations, that simply evaporated when the civilization that nurtured it transformed or fell. Their loss is not just historical, it is a potential library of resilience we can no longer read. This leads to the most profound and unanswerable of our questions, the line between intention and happy accident. When a master builder carved the gentle Entasis into a column, was he thinking, this curve will better distribute bending stress during an earthquake? Or was he solely focused on making the column appear powerfully straight to the people approaching the temple, with the seismic benefit being an unintended gift of that optical refinement? When the community dug a vast moat around Angkor Wat, were they managing the water table to stabilize sandy soil against liquefaction, or were they solely creating a symbolic ocean of myth? The most compelling answer is likely a blend of both. These builders operated in a world where the practical and the sacred were woven from the same thread. A rule of proportion could be a divine mandate from the gods and a proven blueprint for stability. A ritual that enforced a waiting period for the foundation was both a spiritual purification and a critical phase of soil consolidation. Their genius may have been this holistic vision, where solving for beauty, symbol, and community need naturally yielded solutions that also solved for survival. They may not have articulated the physics of energy dissipation, but their cultural and aesthetic principles, refined by trial and error over centuries, inherently led them to it. So the investigation closes not with a full stop, but with an open hand. We have mapped the principles of the dance: flexibility, damping, isolation, and mass. We see them echoed in our most advanced engineering today. Yet the ancient temples retain their aura, not because they are magical, but because they are holistic. They represent a conversation with the earth that was measured in lifetimes, not in project timelines. They challenge us to wonder, in our quest for universal codes and standardized materials, if we have lost the art of listening to the specific song of a place. The final, lingering question they leave us with is not about stone or mortar, but about time and attention. What might we build if we, too, designed for the next 1,000 tremors? And not just the next one. The enduring lesson of these temples is not a single trick, but a complete philosophy of resilience. Their builders mastered a profound truth, that survival in a dynamic world requires flexibility, not just strength. They engineered systems that dissipated destructive energy through friction, rocking, and sway, that isolated precious structures from violent ground movements, and that used smart geometry to direct forces away from points of failure. This was not a fight against nature, but a sophisticated collaboration with it. They built for the dance, not the standstill. In our modern pursuit of ever taller, ever more rigid structures, this ancient wisdom offers a crucial counterpoint, a reminder that true sustainability and resilience might require us to embrace a little give. To design systems that can bend so they do not have to break. These stone giants ask us to see ruins not as static relics of a lost past, but as dynamic, enduring lessons. They are not simply old buildings. They are the longest-running experiments in structural survival the world has ever known, and their continued presence is the data. Whispering across centuries that the most intelligent way to endure an uncertain future is to learn how to move with it.